If you recall, yesterday we calculated a vector, a line integral. If you would recall, I'll edit that out. No, I won't. If you would recall, yesterday we integrated a vector field over two different paths. The two different paths started and ended at the same place, but they followed a different path. The first one was just a line from 1, 0 to 0, 1, and the second one was a quarter circle from 1, 0 to 0, 1. And we were not surprised at all that we got different values for each of those two line integrals. We evaluated them at a different set of points. Assuming that I did those correctly, because I planned for them to be different values. On the next set of problems, so we integrated, so you calculated a line integral of a vector field along two different paths. Those two different paths had the same starting and ending points. We ended up with two different values. The integral over C1 was 1/2, and the integral over C2 was 1. So we ended up with two different values. I didn't finish the integral in the second one along the quarter circle, but I did kind of shorten the amount of work that I needed for it. So this is not surprising. We're integrating over a different path. Of course, we're going to get a different result. So we integrated over a different path. So of course, we're going to get a different result, right? Well, what happened in the next problem? So thinking back to the problems last week. Oh, of course, I didn't open them up. Is it this one? So thinking back to the problems last week, here, the second problem, the problem from Thursday, we had a different vector field along the same two paths. What happened on these line integrals? So then in the next problem, oh wow. When we integrated this vector field along the same two paths, so C1 is the line segment. And C2 is the quarter circle with the same start and end. What happened when we calculated these two line integrals? What was different about this problem, problem 1, 2, 4, where we had what made this problem different than problem 1, 2, 3? Sentence is difficult today. cannot make words into coherent thought. What value did we get for the integral over C1 of f dot dr? And what value did we get for the integral over C2 of f dot dr? I know y'all are thinking, what do you mean we? You weren't here. What did y'all get for each of these? We have two different paths, the same starting point and the same ending point. Did something different happen on this problem that's made it stand out from the previous problem? Let's take a look. So first of all, we have a much simpler vector field. We have xi plus yj. We just got a bunch of vectors pointing away from the origin. So a much simpler looking vector field. Vectors just pointing away from the origin. It's kind of an exploding vector field. So let's take a look at what we're going to get for our line integrals. We have evaluate the vector field at xi plus yj. So we're going to integrate. Our first parameterization for C1 will go from 0 to 1. F evaluated at all these points will look like xi plus yj. So x is 1 minus ti. Plus t times j. There's the vector field evaluated at all the points. We find the dot product of this with r prime, or dr. Which is negative I plus j dt. So we're integrating yeah. Oh, thank you. I wasn't trying to keep the line integral secret. My computer just doesn't read my mind anymore ever since the incident. I'm just kidding. It never read my mind. So we multiply by -1, we'll get t minus 1 plus t. So t minus 1 in the dot product, we'll have 1 minus t times -1 will be t minus 1, and then t times 1 plus t. So 2t minus 1 dt evaluated from 0 to 1. So we'll have x squared minus x evaluated from 0 to 1, which is going to be 0. Let's take a look at integrating this vector field over C2. So the integral over C2 we'll use the same parameterization that we had yesterday. I'll leave a space. And we'll say R2 of t will be cosine of ti plus sine of t times j. And then t will go from 0 to pi over 2. We'll use the easiest parameterization of that quarter circle that we could think of. R2 prime of t is going to be derivative of cosine is negative sine, and derivative sine is cosine, just like it was yesterday. And if I want dr, I multiply all this by dt. So that's where the dt is going to show up and turn this into a simple integral. So my vector field is still just going to be R2, which is with x and y. And we'll integrate from 0 to pi over 2. And we'll find the dot product of this with the dr, which is going to be negative sine of t I plus cosine t j dt. So we're still integrating from 0 to pi over 2. And I find the dot product of f at r and dr. So that's going to be cosine t times negative sine t, and then sine t times cosine t. So we're going to integrate the function 0 from 0 to pi over 2 and come up with 0. So in this example, we evaluated the line integral. We calculated the line integral of the vector field along two different paths, but we got the same results. So that's what we want to point out here. Before, we integrated along two different paths and got different results. Here, we integrated along two different paths and got the same result. In problem 123, we got different results when we integrated along different paths. In problem 124, we got the same result when we integrated along different paths. So the question, since I wasn't here, did you discuss why we got the same result in this case where we got different results in the previous case? Did that come up? What made this problem different? So the difference here was that there's something different about this vector field than there was about the previous vector field, except for the fact that I gave them the same names. I kind of George Foreman myself by just naming all my vector fields F. So So the difference, the reason we got the same result here and different results on problem 1, 2, 3, is that the vector field, one vector field has a characteristic that the other one does not. So the reason that this happened is that this vector field xi plus yj is a path independent. It's a gradient field. So the vector field f xi plus yj is path independent, or we say conservative, or we say it's a gradient field. So when we integrate a linear, when we calculate a line integral of a vector field along two different paths, and the vector field is path independent, all that matters is the endpoints. The other word for the path independent is conservative. And this is because this vector field is a gradient field. When you're dealing with a gradient field or a conservative vector field, which is a path independent vector field, all that matters is the endpoints. The path doesn't matter. All that matters is the endpoints. Since the path C1 and C2 had the same endpoints, that was all that mattered. Because this vector field is path independent. It is a gradient field. When we say that the vector field is a gradient field, that means it is the gradient of some function, some scalar function. That the gradient field has a potential function. So when we say that the vector field is a gradient field, that means that it's the gradient of some potential function f, some scalar potential function f. It's just a scalar function. And it's not difficult to see in this case what the potential function is. The derivative with respect to x is x, and the derivative with respect to y is y. So in this case, if f of xy is a half x squared plus a half y squared, then the gradient of f is the partial with respect to x I plus the partial with respect to y j. That's why I picked this one, so I could easily find the gradient, even at 8 o'clock in the morning with insufficient coffee to process vector calculus. The vector field that we had in problem 1, 2, 3 on Wednesday is not a gradient field. Let's see, what was it? So the vector field field from problem 1, 2, 3 is not a gradient field. So it is not path independent, so it is not conservative. We could just do that. We could check this by just messing around with it. We don't have any fancy tools for this. But if the partial of f with respect to x is minus y squared, so this says that the partial of some vector field with respect to x is minus y squared. That says that f should be minus xy squared plus some function of y, y only. In this case, since we're dealing with partial derivatives, a function just of y will look constant when we take partial derivatives with respect to x. So our potential function will have to look like minus xy squared plus some function purely of y to be the constant. The partial with respect to y is going to be xy. So that tells us that any potential function will have to look like 1/2 xy squared plus some function of just x for the same similar reason. A function of just x will look like a constant with respect to y. The problem is I've got these two different terms. I got this 1/2 xy squared, which is different than a minus 1 xy squared. There's no way to build just one function f out of these two functions. That function of y, the thing that doesn't match is not just a function of y. Let's say not a function of just y. And the same thing happens with the minus xy squared. That's not just a function of just x. If we look at the components of the vector field and think of those as partial derivatives, we can go backwards and construct our potential function. Since the vector field minus y squared plus xy, j minus y squared I plus xyj does not have a potential function, is not a gradient field, therefore it's not conservative. So it's path dependent. So we got different values for the line integral. Good question. We can also note that the second partial derivatives are not equal. So or the mixed partial derivatives would not be equal. So if we look at our vector field f, if there's some vector field, some potential function f at xy, and we want the gradient of f to be the partial of f with respect to x, I'm going to use the other notation. So if these two first partial derivatives came from the same function, then the mixed second partials must be equal. So if I look at fx and I find the derivative with respect to y, and I look at fy and find the second partial with respect to x. If we started with one function, the mixed second partials will be equal. If we start with just one potential function, then the mixed second partials would be equal. But they aren't in this case. So when our vector field if I look at the partial of this minus y squared with respect to y, it's already with respect to x. I'm trying to find what the second mixed partial would look like. We get 0. But over on the other side, on the other component, if we look at xy and take the partial with respect to x, because it's already partial with respect to y, take the partial with respect to x, we get y, and these two things are not the same. So there is no potential function f. So the point of the first problem was to get practice calculating line integrals along different paths, which comes down to practicing parameterizing a curve. The second problem, problem 124 from Thursday, that problem was about having calculating a line integral of a conservative vector field and seeing that we ended up with the same result. Actually, seeing that we ended up with the same result, noticing that was different than the previous one. Then the third problem would have been about utilizing our fundamental theorem of calculus as it applies to line integrals. The fundamental theorem of calculus for line integrals applies to integrating conservative vector fields, integrating gradient vector fields. Now, this is where C is any path from point P to point Q. The path doesn't matter because we're integrating a vector, a gradient field. All that matters is the endpoints, and what we do is what we always do for a fundamental theorem of calculus. We integrate over a set by evaluating the antiderivative at the endpoints. That's weird to say antiderivative. I'm just going to say potential function at the end minus the potential function at the beginning. Note that we called this the fundamental theorem of calculus for line integral. And note that it has the same structure of a fundamental theorem of calculus, specifically this part of the fundamental theorem of calculus. If we integrate a derivative, if we integrate a rate of change over an interval, we get the amount of change in the function on that interval. We just look at how the function changes on that interval. Integrate a derivative on a set by evaluating the function at the boundary of the set. We're going to integrate derivative by evaluating the function at the boundary. So in our original fundamental theorem of calculus, f prime is the derivative, f is the function. The set is the interval from a to b. The boundary of that set are the endpoints a and b. And we're doing the same thing with a line integral. When we integrate the gradient, that's standing in as the derivative of the potential function. The set is any path from point P to point Q. Point P and point Q act as the boundary of that set. General structure for something that we're going to call a fundamental theorem of calculus is that we integrate a derivative by evaluating over a set by evaluating the function at the boundary of the set. So when we get to the problem on 1, 2, 5, we've got a vector field. We want to find out if there's some potential function. If we're dealing with a gradient field, then all we have to do is evaluate the gradient field at the endpoints of our path. Sorry, evaluate the potential function at the endpoints of our path. And since all three had the same endpoints, we just have to do it once. Oh, wait, the third one, I changed the direction. I went for so you'll have to do, instead of f of q minus f of p, you'd have to do f of p minus f of q, but you know what's going to happen in that case. Any questions? How's everybody? I have lots of questions. That was a struggle to get through. I don't know what's wrong today. I don't know if this is a more coffee problem or a less coffee problem, but I know what solutions I'm going to apply. So look at that structure with the 3 problems from last week. That was the structure of the 3 problems from last week. Practice parameterizing a curve and evaluating a line integral. Number 2, recognizing that 2 different paths might produce the same result. Then having it pointed out that that's because that is a particular kind of vector field called a gradient field. And gradient fields are conservative or path independent. And then in problem 3, we have learned about the fundamental theorem of calculus for line integrals. So we just find the potential function and evaluate at the endpoint. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.